Thank you very much. Thanks, Azalia and Brajesh, for the kind invitation. It's my first VeTSS conference, and I thoroughly enjoyed it. I learned a lot, and I congratulate you for the great work that you have done in this project. What I'm presenting here is a series of work with lots of co-authors. I counted 6 papers that we have written in the past 6-7 years on the topic. So although my name features here, most of the work has been done by others, and the credit goes to all of them. In particular, I stole some slides from some of the co-authors. So the ones I could recall, I've cited here. I do mention the papers underneath as citations in my slides. But of course, the remaining mistakes are mine, and the credit goes to all of those people who contributed to this work. And my work has been funded by lots of different projects, including the QAssure project that you heard about in the last talk. In fact, it's quite challenging for me to give this talk because I have vested interest both in the topic before me and the topic after me. And the worst thing you can do to an academic is to tell them not to speak about something, or not to speak at all. That's even worse. But anyway, I will talk about automata learning for the remainder. Before I start talking about automata learning, I will talk about the research philosophy of our group and our research mission. By the way, please stop me if you have any questions. I did not assume any pre-knowledge, so if there is anything unclear, it's my fault, and I would very much appreciate if you could ask questions and engage and make this interactive. So the mission of our group is to use mathematically founded, rigorous techniques in order to ensure safety and trust in autonomous systems of various kind. And safety is well understood. We have worked on safety for many, many years. There are safety engineers out there whose only job is to build safety cases for different types of autonomous systems. Trust is the new name of the game, and it's a much softer thing to get your hands on. So one possible definition for trust is the user's belief that the system is going to be helpful and safe, particularly in very challenging scenarios. So if you're willing to put your child in a car, in an autonomous vehicle, to bring them from home to school, for example, and if suddenly the car takes a very sharp turn and you still trust that the car can handle it, then you're trusting the system. And it goes already from this example that trust is not necessarily a positive thing. It can be very negative, actually. If you overtrust a system that is not trustworthy, then you're going to harm yourself, right? So much of what we are doing is to calibrate the level of trust that the users have to the actual trustworthiness of the system, right? And for that, we are working on many different factors that can contribute to this calibration of trust with trustworthiness. One is technical transparency, and much of the work that we have done in automata learning is in that direction. So how can we learn models from a black box and also present it in an understandable manner to the user so that they know what's going on in that black box, right? So much of the rest of the technical talk is actually about building models and building models compositionally in an understandable and succinct manner. But also that's about learning about the design intentions, but also at runtime, if you can learn about the runtime decisions of the system through some sort of explainability, provably correct explainability, then you're also contributing to establishing the right level of trust in the system. If you have understandable evidence of safety and security, or lack thereof, you're also contributing to the calibrated trust. And also, if the system can communicate in a human-like manner, also taking into account the type of knowledge, the type of expectation that different user groups have, then you're contributing to the correct calibration of trust and trustworthiness. And much of this research happened in a project that ended about less than a year ago, about 6 months ago. It was an investment by UKRI in an umbrella project called Trustworthy Autonomous Systems, TAS. And I was in charge of the verifiability part of the TAS project, which was a collaboration among 8 different universities. Some of the logos you see here, the logo of Lancaster is missing because they joined later in this node. One of our researchers moved to Lancaster, and as a part, Lancaster became a member as well. But the vision of this project was to bring different researchers from completely different disciplines that would otherwise not talk to each other and build some sort of medium that translates their different languages to each other so that they can understand the implication of the design decisions they make in their own field on the entire design of the autonomous system. So we had people who were specializing in psychology. We have people who are specializing in mechanical engineering. We had software engineers. We had AI experts, and they all spoke very different languages. And the goal of this project was to build some sort of communication medium, hopefully formal, with some sort of mathematical underpinning, so that we can translate the effect of the design decision that the mechanical engineer makes in shaping the robot in a certain sense into the human machine interaction that the psychologist is analyzing, and then vice versa, right? And for that, we built some sort of workflow. So this was the structure of the project that I showed in the previous slide. But for that, we also built a workflow that would start from common case studies. So we had 3 large case studies across the project. It was a £3 million project, quite a large project with 8 different partners. So we already from the start, we agreed on 3 common case studies. And we used different levels of abstraction to facilitate communication. So we started specifying different aspects of the system in a language with some sort of mathematical underpinning. We worked on different types of verification and testing, simulation, runtime monitoring, formal verification, theorem proving. And also we had physical implementation of all 3 case studies in place. Some of them were kind of being developed as we did the specification and the verification. Some of them already existed before, and we were kind of testing them while we were running the project. This allowed us to have the entire team working on common case studies and interact with each other on those common case studies and try to establish a more meaningful dialogue among all the experts in the project. Here are some of those case studies. So we had a firefighting drone from Leeds. You see, Real Robotics is a spin-off from Leeds that was developing that drone. So there was an older version of this drone, but we built it actually from the bottom up throughout the project, through the 3 years of the project. And the results are now being concluded for publication. We did all those different testing verification techniques that we developed in the project on this drone. And all the work packages had something to contribute to the development of the drone. On the other side, you see a robotic arm, which was used in a case study used for healthcare. So it was helping stroke patients to wear a garment, for example, after they come out of shower. And another case study that we had was this doll called Caspar from Hertfordshire, which was developed for autistic children, and different case studies, different work packages contributed to different aspects of development of Caspar further. And there are lots of publications, for example, on trustworthiness, calibration, but also on the different verification techniques we developed in the project. The results are mostly available through the project website. So if you are interested to see what happened, the technical results as well as the annual reports of the projects are on the verifiability website. And also we had a YouTube channel where we hosted, I believe, about 100 public talks by experts from different domains every week throughout the project. We also contributed to policy. So we talked to policymakers. So this is the German, which one is it? This is the German Minister of Transport. We met at OECD, and then we talked about policymaking around AI in autonomous vehicles. But also we contributed to different pieces of policy papers and other pieces of work that was carried out through the project. So that kind of summarizes what we did in the past 3 years in the project. And the project has now come to an end. We are seeking subsequent funding to sustain the momentum we gained with different partners. That was that. So let's now dig deeper into the technical topic of the talk. Are there any questions before I move into the technical part? No, okay. So it will be about automata learning, and I don't assume that you know what automata learning is about. So I will first give a very quick kind of a crash course on automata learning, and then I will zoom into 3 different extensions that allow automata learning to scale in time, to scale in space, and also to scale in terms of system size. So let's start with automata learning. Why is this interesting? So I'm mostly interested in testing, and very often testing starts with some sort of model. It could be the Oracle problem that Alistair mentioned this morning, right? So you need something to tell you what the correct behavior is. And that is very often missing. So the starting point of testing is very often missing. And if you have a black box implementation somewhere, you could learn a model of that black box implementation and abstract it into a model that you could use, for example, for testing. So that was my starting point when I got interested into automata learning. But I also saw later on that this could be very effective means for building transparency into a black box system where the manufacturers have very little incentive to be transparent, right? Lots of black box systems out there are built as a black box, and the manufacturer doesn't give you enough information how they built it. So using automata learning, you could build transparency into it. I will give several examples through the talk. So what you could do in automata learning is to reverse this. Basically, you start with an empty specification, right? And you will see an example very soon. I can't point here probably, or can I? Absolutely. Yeah. So you start with an empty specification, right? You generate some sort of chaotic number of test cases that, when applied on the implementation, will give you some more information about the possible outputs of the system to those chaotic test cases that you have posed. We call them queries to the system. And you incorporate them into the next iteration of the model learning, where you summarize everything that you have learned in the first set of queries that you have posed in terms of some sort of model. And in this case, the model will be a finite state machine or an automaton. And you repeat this until, by posing more queries to the system, you will not learn anything more. So this has been formalized, and there are some survey papers, and this is a paper in the Communication of the ACM, appeared in 2017, I think, by Fritz van Drager, which nicely summarized the results up to that point in a very didactic manner. So you can read more about it, and there is also a YouTube video attached to this paper that you can watch later on. So this was formalized by Dana Anglin in 1987 in an information and control paper in an algorithm called L-star. And L-star assumes that you have something called a minimally adequate teacher. A minimally adequate teacher is a teacher that has access to the system under learning, and the learner can pose queries to this minimally adequate teacher. So it can first pose queries called membership queries. It can ask the system, if I give you this input, are you going to accept it from me or not, if you're learning a normal automaton? Or if you're learning a mealy machine, for example, if I give you this input, what would be your output? Those are the type of membership queries that you can pose to a black box, right? What would be your output if I pose this particular input to the system? And the teacher will basically forward these membership queries to the system under learning, and will give you the corresponding output. So the teacher doesn't do much if you're posing membership queries, right? However, after you pose a number of membership queries, you guess something about what is inside the black box. So I will use a windscreen wiper as an example. You will see that in the next slide. And after you pose some queries, you think, oh, what is inside the windscreen wiper controller would be something like this. An automaton that, if the sensor senses rain, it will produce a 0. If you switch the windscreen wiper on, it will produce 1, for example. And it will all go back to the same single state. Then what you can do after you have a hypothesis about what is inside the black box, you can ask your teacher, is this what is inside the black box or not? So that's a very heavy query that you're asking. You're asking whether what is inside the black box is equivalent, using some notion of equivalence, for example, trace equivalence, language equivalence, input-output equivalence, to what you have hypothesized here, right? And then the teacher has to do a lot of work to find out whether what is inside the black box is the same as what you have hypothesized, typically using some sort of conformance testing algorithm, okay? And there are lots of conformance testing algorithms out there that could do the job of an equivalence query for you, right? So that's what Dana Anglin formalized many years ago, and I will give you a quick, and based on what you get from the equivalence query, you're going to refine your hypothesis, maybe pose a few more membership queries, and then do the same equivalence query in a number of rounds until you get a provably equivalent system based on the conformance testing that you pose to the system under learning, right? And then your algorithm terminates. And then Dana Anglin showed that this terminates in a polynomial number of queries in total. Any questions so far? Anything that is unclear? No? No? Okay, good. So let's look at a quick example. So suppose I have a windscreen wiper that has rain and switch interval as 2 inputs, and it can produce 0 and 1 just for simplicity as outputs. Of course, more complex systems are much more complex in terms of input and output alphabet, but Let's assume we are doing that. So the first thing you do is to pose a number of simple queries. So you assume that you have not posed any queries, so the system is in the initial state. So that's what epsilon means here. You have not posed any queries before, right? And you ask the black box, what is your output if I pose rain to you? Okay, so this is what is inside the black box. We don't know what is inside it. We are just posing queries, right? And if you pose rain to the system, it will produce 0. That's why we just denote that by 0 here. So if you're in the initial state and you pose rain as an input query, then you get 0 as output, right? And likewise, if I reset the system to the initial state and then pose switch interval and ask the system, what would be your output? It will say, okay, if I do switch interval, then I will produce a 1, right? And I just note that here in my table. And everything is organized in a table in Dana Anglin's L star. There are more advanced algorithms that use other data structures, but that's the vanilla type of automata learning that you can start with, okay? So that's your first attempt to learn the system. And, so the first attempt would result into this automaton. It says, if you're in initial state, you pose rain, you will go to the same state and do 0 and get 0 as output. If you do switch interval, you'll go to the same state and get 1 as output. You could test whether this is a good hypothesis or not by looking just one step ahead and checking whether if you go one step ahead, you will see the same input-output behavior or not. So let's do that. So if I go one step ahead and instead of starting from an initial state, I start from rain and do another rain, I see the same output. So this suggests that probably by doing a rain, I'm staying in the same state as the initial state. If I do a rain followed by switch interval, if you look at the black box, it will again produce the same output. So this suggests that doing a rain is probably not going to change my state. And so far, I haven't discovered anything new apart from what I've seen in the initial state, right? However, if I do a switch, if I reset my system and I do a switch interval followed by rain, I suddenly see a different output that I hadn't seen before, right? So suddenly posing a rain query to a system that has seen a switch interval will give me a 1, which I hadn't seen before. And this suggests that no, my hypothesis is not good enough because I have discovered a new state. And what you will do, you would push this up. So this is a kind of inconsistency in your table. You will push this up. You will start from a new table in which epsilon and rain will be the same state, while switch interval will be a new state. That will be your new hypothesis. You'll look one step ahead. If looking one step ahead doesn't give you any new information, then you will pose an equivalence query to your teacher, and the teacher will tell you whether this is good or not, right? And you will continue this over and over until you stabilize, you reach a fixed point and you don't get any counterexamples from your teacher. Okay? So that was, again, a recap of L star. Nothing new here, but I hope it clarifies all the technicalities behind it. Any questions so far?
Does this process terminate? Can't you learn something recursive?
Because the assumption is that what is inside the black box is a finite automaton, right? And Dana Anglin proved that this terminates in a polynomial number of queries. There are some tricks about her proof, and there's a lot to discuss, but it does terminate, and it does terminate in a polynomial number of queries. Yeah? Good. Okay, so these are the conditions that you check, and after the conditions are satisfied, you pose an equivalence query, and then the teacher will tell you yes or no. If it tells you no, it will give you a counterexample, and the counterexample helps you refine the table further by posing more queries. Okay? So that's how things work. So you change your query until you learn what is inside. What you can do for equivalence queries is conformance testing. There is a whole literature. There is a very nice book, LNCS volume, on conformance testing. If you want to learn more, I can give you also more references. And there is also a whole literature out there. These are reasonably recent papers from a couple of years ago, where they extend L star for stochastic systems, for dynamical systems. And we have been working also in this domain, extending L star for different types of semantic models than just finite automata. So there is a lot out there that you can use in practice. Now, what I will be talking mostly in this talk, in the remaining 10 minutes, is extensions of L star in time, meaning that if my system has evolved over time, how can I relearn the system without posing the same queries over and over again? How can we learn evolution of the system over time? How can I learn different configurations of the system, different versions of the system that have been compiled, for example, using different options? And how can I parallelize this system so that I can scale it up to very large scale systems? So let's start with time. Suppose I learned this thin screen wiper system first, and then the developers started developing the system further. They introduced a new feature into the system. For example, there is something called switch permanence, right? How can I relearn the system without posing all the queries I've posed in the past, and save a lot of effort in kind of reusing the old structure that I had learned? Of course, the implementation may change the old behavior, may introduce new behavior. So what I need to do first is to figure out what kind of states are still valid, what kind of distinguishing sequences that I have are still valid, and reuse them as much as I can. So we did that. First of all, this is a field that existed before us. So there are at least 2 influential papers that did this before we started our research. And we built definitely upon the ideas from these papers. We implemented an algorithm. I will explain very briefly what the ideas of the algorithm is in just one slide. And we asked, how efficient are they in relearning a system? Are they more efficient than relearning from scratch or not? And how sensitive are these algorithms to the evolution in time? So how robust are they if I implement some changes in the system, right? The idea of the algorithm is very simple. The first thing we do is to extend the input alphabet to the new inputs that have been introduced into the system, right? And see what parts of the outputs remain valid in my table, okay? So we extend the columns of the system with the new inputs that have been introduced. Also, we check whether any of the old states of the system now collapse into the same because of the changes that the developers have made in the system, right? One more thing that we check is whether the combination of input and output that would distinguish old states are still valid and are still distinguishing the old states that were different before. So we use different search algorithms to find these basic information out from the evolved system. And once we find out, we basically rerun, for the rest, we rerun the plain L star. So whether we need new experiments to distinguish states or not, that we also learn, and then we run the plain L star. We implemented that and we applied to 25 years of OpenSSL, so relevant to the subject of this conference, right? So we started from the initial version of OpenSSL implemented 20 some years ago, and then we relearned every version using plain L star, using our own algorithm and using the state of the art and compare them to each other. So the goal was to find out how much we save by using our algorithm. And the results were very interesting. So this is our algorithm. Let me remember. So this is the state of the art by Shrigina and others. This is our algorithm. And if you have something negative, it means that you're losing with respect to L star. If you have something positive, it means that you're gaining. And what we showed is that, first of all, you always gain by running our algorithm over time, while with the state of the art is a bit shaky. And also, it's quite robust with respect to development time. So you are not losing a lot by using a pretty outdated version of the algorithm. The details are to be found in the original IFM paper that we published 5-6 years ago. Then what we did was to look at evolution in space. So suppose you have many different valid versions of the algorithm currently in place, because you can configure the system in many different ways. How can we summarize all this information into one automaton? And whether this summarization will lead to a succinct model that is readable by human user, by summarizing all the variability into one model, annotating it with the different configurations. And also how sensitive this is to the number of samples we make from this configuration space. So what we did, we basically took a plain automaton and we annotated the transitions of the automaton with propositional expressions specifying what configurations have been used to reach this transition, right? So this is our semantic model. And our goal is to extend L star algorithm to not only learn the transitions, input and output transitions, but also learn the propositions that are attached to them, under which configurations these transitions are enabled or disabled. And that we do by running different versions of L star using different configurations. To generate these configurations, we use different algorithms for sampling the configuration space, and then we summarize them using an algorithm on top that attaches to the transitions of the individual automata these propositional expressions. Again, the results have been reported in this empirical software engineering paper. And what we did, we applied this to a number of case studies, and we measured how much, so these are the different case studies, and we measured how much we gain by summarizing the information into one model. So this is showing the number of transitions in the combined model, which we call featured finite state machine, compared to the individual models before combining them into a single model. And you see there is a reduction in all cases, sometimes very significant reduction in all cases when you combine this information and use this algorithm on top to attach propositional expressions to the different transitions of the model. And the effect size we have measured, and this showed that there is a significant gain by running our algorithm on top. And also what we showed that to do this, you don't need to do a huge number of samples. So even if you do like pairwise or three-wise sample of your configuration space, you can already gain quite a high efficiency across all the case studies that we have done. So beyond 3, you hardly see any increase in accuracy of the model that you have learned. So by taking either pairwise combination of parameters or three-wise at most, you learn everything that is there to learn from the system. Now, this was the third bit, and we extended that to also combine this with adaptiveness, so learning from the past experience so that you don't pose the queries from scratch. And that was published in SPLC 2022. The final bit is to parallelize all of this so that you don't learn one flat model for the entire system, but while learning the behavior, you also learn about the structure of the system. So suppose your system is composed of like 10 different parallel components. How can I learn those 10 parallel components while learning what their behavior is? And that's, I think, a very crucial step, because what Fritz van Drager, for example, observed in his paper is that automata learning does not scale beyond 100 inputs and outputs. And what we have seen here is scaling of the order of 5 or 6 orders of magnitude. So 10 to the power of 5, 10 to the power of 6, we can learn using these type of parallelized algorithms. Compared to only like 100 states, 100 inputs and outputs in flat algorithms. So what is this based on? Is based on the notion of parallel composition. Suppose I have 2 automatons with input and output behavior. If I compose them in parallel by just interleaving the transitions, I'll get such a model, right? So you can see the A's and B's on one side being interleaved with C's and D's on the other side, and you get this type of diamond structure in the flattened model. This is all nice, and you can use L-star to learn this instead of these. But if you do a few of these components, suddenly the model gets very cluttered and very, very big. So you cannot learn this properly using L-star. And this immediately explodes beyond what is possible using L-star. So what we are trying to do is, instead of learning this spaghetti thing, we are trying to learn these components by parallelizing L-star and kind of distributing the task of L-star by learning what the alphabet of these individual components are. Unfortunately, given the time, I can't go into the details, but basically we are replacing the learner with a number of parallel learners, but we start from very simple learners and we refine their alphabet while we are learning the behavior. So we identify what kind of dependencies there are between the alphabets of the different learners, and then we merge them together until we reach some sort of minimal set of learners that can learn the entire system. That was the idea. Unfortunately, I don't have time to go through it, but for example, we applied it to an automotive case study, and we showed that we gain huge amounts of saving if you do this type of compositional learning, which is this orange line, compared to the plain vanilla L-star if you just learn one flattened model. That was published in FOSAX, and the improvement increases by the number of components. So the more number of components you add to the system, you gain more by running all algorithms compared to plain L-star. The basic algorithm was published in FOSAX 2023. This was only for interleaving parallel automata, but this year in Concur, we are publishing an algorithm where we extend this to full composition of any type of automaton that you give me. So you can have synchronization among all those different automata, and it will learn not only about the possible interleaving, but the possible synchronization of those automata as well. And that is going to appear this year at Concur in a couple of months in Belgium. And that was a work of about 3 years that we spent on finding out how to learn about the synchronization behavior automata while learning about the individual components. And we showed that if we combine all of this, you can gain up to 6 orders of magnitude of saving if you have sufficiently many parallel components in the system. And this is implemented in a tool called Koala. So with that, I would like to conclude. I started with the basic idea of automata learning. I started with basic L star. Then we developed an adaptive version of L star that would learn new versions of the system over time and reuse queries from the past to know what is still valid and what needs to be relearned. Then we learned about different configurations of the system, how we can combine different configurations of the system into one succinct model. And finally, probably much more influential, much more impactful in the future is how to parallelize this process of learning automata, both in terms of interleaving parallel composition, but also in terms of synchronizing automata, where there is possible synchronization among the components. And with that, I would like to conclude. Thank you very much.
Great. Yeah. We'll have to read your papers. There's time probably for one quick question before we move on to the next talk.
Yes,
yep.
Please.
In the setting of your autonomous vehicles, to what extent do you trust your equivalence queries to catch corner cases?
Right. Okay. So we haven't applied this to autonomous vehicles as yet. The technology is very much in its infancy, although it has been around for about 2-3 decades. We need a lot of abstraction to learn about actual systems. So it has been mostly applied to protocols so far. So they have learned TCP, SSH, SSL, these type of, and they found significant bugs in them. Like in the Dutch passport, for example, they found mistakes, they found bugs in. So these are relatively small systems. In order to scale this up, we definitely needed this compositional learning, and we haven't applied it. So I haven't applied any of this to any autonomous vehicle yet. It's in our horizon because we are learning, for example, the emission behavior of normal vehicles, not autonomous ones. And we want to learn some model of the powertrain controller of the system, which then involves also abstraction of the continuous variables into some discretized one. But we haven't done any of that yet. It's in our future work to do it.
Okay, thank you very much.
Thank you.